Imagine being a titan of industry, a name synonymous with manufacturing might. Ford, Volkswagen, General Motors. For a century, you set the tempo for the global economy. Your orders moved mountains of steel and rubber. Then, one day in 2021, you pick up the phone to order a handful of silicon chips, components that cost a few dollars each, and you're told to get in line, behind a teenager buying a new smartphone. This wasn't just a long wait. It was a fundamental status collapse. The global automotive industry, a sector that represented trillions in market value, found itself completely powerless. Its multi-billion-dollar assembly lines, the marvels of modern manufacturing, ground to a halt for want of a few microchips. At Ford, thousands of its most profitable F-150 pickups sat idle in vast parking lots, nearly complete but unsellable, waiting for a part smaller than a postage stamp. In Germany, Volkswagen's main Wolfsburg factory, the heart of its global empire, saw production fall to its lowest level since 1958. The entire industry was paralyzed. How did this happen? How did the giants who built the 20th century find themselves begging for capacity from a single, highly specialized company in Taiwan? This story isn't just about a supply chain crisis. It's the story of a humbling wake-up call, a moment when the old guard of manufacturing was forced to confront a new reality. It's the story of how the global automotive industry, which once viewed semiconductors as simple commodities, suddenly found itself at the mercy of Taiwan Semiconductor Manufacturing Company, or TSMC. And it's the story of how, as of mid-2025, they are being forced to fundamentally change their strategies to survive in a world where the car is no longer just a machine, but a data center on wheels. For decades, the automotive industry operated on a principle of near-perfect efficiency, a manufacturing philosophy so successful it became a business school gospel, just in time, or JIT. Pioneered by Toyota, the model was elegant in its simplicity. Parts, from engines and transmissions to door handles and window switches, were delivered to the assembly line precisely when they were needed, not a moment sooner or later. This approach minimized the need for vast, expensive warehouses, reduced inventory costs, and allowed automakers to be incredibly nimble. They were the conductors of a massive, finely tuned global orchestra, with thousands of suppliers marching to their beat. The system worked flawlessly for mechanical components. A steel supplier could ramp up production relatively quickly. A tire manufacturer could add an extra shift. In the world of atoms, supply was elastic. The core failure of 2021 was not in the JIT model itself, but in the automaker's assumption that all components are created equal. They treated semiconductors, the brains of their vehicles, like any other commodity. They applied the logic of an elastic mechanical supply chain to the highly inelastic, capital-intensive world of high-tech fabrication. It was a profound category error, and it would prove to be a catastrophic one. Semiconductor manufacturing is a world away from a steel mill. Building a new fabrication plant, or fab, is one of the most complex and expensive construction projects on Earth, taking years and tens of billions of dollars. Even ramping up production on an existing line has a lead time of 3 to 6 months, a lifetime in the fast-moving auto industry. Fab capacity is a finite, precious, and incredibly expensive resource. It cannot be turned on and off like a spigot. This fundamental misunderstanding led to a fateful decision in early 2020. As the COVID-19 pandemic swept the globe, automakers looked at the shuttering world economy and did exactly what their JIT playbook told them to do. Fearing a collapse in car sales, they drastically cut their production forecasts and in turn cancelled their chip orders. To them, it was a prudent, cost-saving measure. To the semiconductor foundries, it was a clear signal. The auto industry was stepping out of the queue. At the exact same moment, another industry was facing the opposite problem. The world, now confined to their homes, went on a historic buying spree for consumer electronics. Demand for laptops, webcams, gaming consoles, and smartphones exploded. Chip makers and foundries like TSMC, seeing their automotive orders evaporate and their consumer electronics orders skyrocket, did the only logical thing. They reallocated every available production slot to their hungriest and most profitable customers, companies like Apple, Qualcomm, and Nvidia. The automotive industry had willingly given up its place in line, and the tech industry was more than happy to take it. The whiplash came in late 2020. Auto demand, defying all predictions, came roaring back. Consumers, flush with stimulus cash and unable to spend on travel or services, wanted new cars. The automakers picked up the phone, calling their Tier 1 suppliers like Bosch and Continental, and placed massive new orders for the electronic components they had cancelled just months before. The Tier 1s, in turn, called the foundries. The response was a deafening silence. The production slots were gone, booked solid for the next 12 to 18 months. The auto industry, accustomed to being the 800-pound gorilla that could command its supply chain at will, had been sent to the back of a very, very long line. The real-world impact was immediate and devastating. Across the globe, assembly lines fell silent. Ford was forced to halt or cut production at 8 of its North American plants. The crisis hit its most profitable vehicle, the F-150 pickup truck, particularly hard. In a surreal scene, thousands of nearly finished trucks were parked in lots across Michigan, Kentucky, and Missouri, complete in every way except for the tiny silicon chips needed to make them run. The company warned that the shortage could slash its earnings by up to $2.5 billion. Volkswagen was plunged into what its then CEO, Herbert Diess, called crisis mode. The company admitted it was unable to build at least 100,000 cars it had planned for 2021. Its iconic Wolfsburg factory, the largest single car manufacturing complex in the world, was forced to cut working hours and ultimately recorded its lowest production output in over 60 years. Between 2020 and 2023, the total production loss for VW mounted to a staggering 2.3 million vehicles. General Motors suspended production at plants in the US, Canada, and Mexico, affecting a wide range of its vehicles. The pain was global. The total cost to the auto industry was estimated at $110 billion in lost revenue in 2021 alone, with over 11 million vehicles cut from global production plans. Another estimate put the total number of vehicles lost between 2020 and 2022 at over 35 million worldwide. The finely tuned, hyper-efficient system of just-in-time manufacturing had spectacularly failed, brought down by a component the industry had never truly bothered to understand. To understand why the automotive industry was left out in the cold, one must first understand the world from the perspective of a foundry like TSMC. And from that perspective, not all chips are created equal. The crisis of 2021 was not just about supply and demand. It was about a fundamental misalignment of priorities, rooted in the technological and economic realities of silicon fabrication. The vast majority of chips in a pre-2021 car were what the industry calls legacy chips, or microcontrollers, MCUs. These are the workhorses of the electronic world. They perform simple, dedicated tasks, controlling power windows, managing airbag deployment, regulating the anti-lock braking system. They are built on older, larger, and fully depreciated process nodes. Think 45 nanometers, 90 nanometers, or even larger. Because the technology is mature and the equipment to make them has long been paid for, these chips are incredibly reliable and, most importantly, incredibly cheap, often costing just a few dollars apiece. For automakers obsessed with shaving every last cent from their bill of materials, these chips were perfect. But for a foundry like TSMC, these chips are an afterthought. The company's focus, its prestige, and its profits all come from the other end of the spectrum. Leading-edge chips. These are the technological marvels built on the smallest, most advanced process nodes, 7 nanometers, 5 nanometers, and now 3 nanometers. These are the chips that power the latest iPhones, the most powerful data center GPUs, and the next generation of AI accelerators. This is where TSMC invests tens of billions of dollars in research and development and capital expenditure each year. This is where they command the highest prices and the fattest profit margins. A look at TSMC's own financial reports from the period paints a stark picture of the automotive industry's place in the customer hierarchy. In the fourth quarter of 2020, as the shortage was reaching a fever pitch, the automotive segment accounted for a mere 3% of TSMC's total revenue. This was utterly dwarfed by smartphones, 51%, and high-performance computing, HPC, 31%. For the full year of 2020, the story was the same. The auto sector contributed just 3% of revenue, a figure that had actually decreased by 7% from 2019. In that same year, revenue from HPC customers grew by 39%, and smartphone customers by 23%. When automakers cancelled their orders, it was a rounding error for TSMC. When Apple or Nvidia called for more capacity, it was a strategic imperative. The power dynamic was never about the sheer size of the automotive industry. It was about its role, or lack thereof, in the semiconductor innovation cycle. The auto industry was a consumer of old technology, while the tech industry was the driver of new technology. TSMC's entire business model is a virtuous and hugely expensive cycle. It uses the massive profits generated from today's leading-edge node, say 5 nanometer, to fund the multi-billion-dollar research and development required for tomorrow's node, 3 nanometer. Customers like Apple and Nvidia are absolutely essential to this cycle. They operate on brutally short product life cycles of 1 to 2 years and are locked in a perpetual war for performance. They are not just willing, but desperate, to pay a premium to get the performance and power efficiency benefits of the newest node first. They are the anchor tenants who place massive, predictable orders that de-risk TSMC's colossal capital investments. The automotive industry, with its long 7 to 10-year development cycles and its painstaking process of qualifying cheap, reliable legacy chips, played almost no role in this innovation engine. They were not funding the future. They were buying the past, often from third-party chip makers who used foundries like TSMC. This made them a fundamentally less strategic partner. As TSMC's CEO, Dr. C.C. Wei, has consistently stated, the company's focus is on meeting the surging demand for its advanced technologies. For decades, the auto industry simply wasn't part of that conversation. They were a low-volume, low-margin, low-priority customer, and in the crisis of 2021, they learned what that meant in the starkest possible terms. The 2021 chip shortage was the end of an era, but it was also the beginning of a new one. The very forces that are now reshaping the automotive industry, electrification and automation, are the same forces that are completely inverting the power dynamic between car makers and chip makers. The age of the car as a simple machine is over. The age of the car as a software-defined data center on wheels has begun. The electronic architecture of a modern vehicle is undergoing a revolution. A traditional internal combustion engine car might have contained anywhere from a few hundred to 1,000 individual semiconductor chips. A modern battery electric vehicle, EV, by contrast, contains between 1,500 and 3,000 chips. But it's not just the quantity, it's the quality and value. The total semiconductor content in an EV can be worth $1,500 to $3,000, roughly 2 to 3 times more than in a comparable gas-powered car. These new, high-value chips are not just replacing old ones, they are enabling entirely new systems. They are found in the complex battery management systems that optimize range and charging, the power inverters that convert DC battery power to AC motor power, and most importantly, in the centralized computers that serve as the vehicle's brain. Cars are no longer a distributed network of simple microcontrollers. As of mid-2025, The industry is rapidly consolidating these functions into powerful, centralized system-on-a-chip, or SoC platforms. These are no longer just chips. They are full-blown supercomputers, and they are at the heart of the new automotive supply chain. The competition to provide this brain is fierce, dominated by the same tech giants that command the data center and mobile markets. NVIDIA Drive. Thor. This platform is a glimpse into the future. NVIDIA describes it as a centralized car computer designed to unify everything from the digital cockpit and infotainment to the most demanding automated driving functions. Built on the company's latest Blackwell GPU architecture, a single drive Thor chip boasts up to 2,000 trillion operations per second, tops, of performance. It is specifically designed to handle the massive transformer models and generative AI workloads that will power next-generation in-car assistance and Level 4 autonomous driving, all on a single, functionally safe platform. Qualcomm Snapdragon Digital Chassis. Qualcomm is leveraging its dominance in mobile technology to offer a comprehensive suite of platforms. The digital chassis is an open, scalable set of technologies that includes the Snapdragon Ride platform for ADAS and autonomous driving, the Snapdragon Cockpit platform for immersive in-vehicle experiences, and Snapdragon Car-to-Cloud services for connectivity and over-the-air updates. It's a holistic solution designed from the ground up for the software-defined vehicle, allowing automakers to mix and match components to create customized, updatable experiences for their customers. The critical point is that these automotive supercomputers are not built on legacy technology. They are built on TSMC's most advanced and most sought-after process nodes, 7 nanometers, 5 nanometers, and soon 3 nanometers. This is the same silicon that powers the world's most advanced smartphones and AI data centers. This technological shift has triggered a seismic change in supply chain dynamics. In the old model, automakers needing 90-nanometer chips and Apple needing 7-nanometer chips were operating in completely different technological and economic spheres. They were not competitors. Now, the new Volkswagen, powered by a Qualcomm Snapdragon Ride Flex SoC, is ordering 5-nanometer chips. The new iPhone, powered by Apple's in-house designed A-series chip, is also ordering 5-nanometer chips. They are now ordering from the exact same menu at the exact same very exclusive restaurant, TSMC's leading-edge fabs. This completely inverts the old power dynamic. Automakers, who used to be big fish in the small, low-margin pond of legacy auto chips, are now relatively small fish in the massive, hyper-competitive ocean of leading-edge silicon. Their order volume, while growing rapidly, is still a fraction of the smartphone and data center markets. In 2024, the HPC and smartphone segments together accounted for a staggering 86% of TSMC's revenue, while the automotive segment, despite its growth, sat at just 5%. Automakers have lost their traditional leverage of scale. To secure the silicon that is now the lifeblood of their future products, they can no longer rely on old purchasing habits. They must adopt the strategies of the tech world to survive. They must get in line, and they must find a way to become a customer that TSMC can't ignore. The shock of 2021 was a lesson learned in the most painful way possible. The old automotive supply chain was broken. The traditional multi-tiered model, where an automaker dealt only with its Tier 1 supplier, who in turn dealt with a Tier 2, who might then contract a foundry like TSMC, was a system that created a dangerous lack of visibility and a diffusion of responsibility. When the crisis hit, automakers were flying blind, unable to see the choke point 3 or 4 levels deep in their own supply chain. In response, a new playbook is being written in real time. As of mid-2025, the strategy is no longer about arm's-length transactions. It's about direct engagement. Automakers are aggressively bypassing the middlemen to forge direct, strategic relationships with the ultimate source of their most critical components, the chip designers and the foundries themselves. Volkswagen, one of the hardest hit by the shortage, has adopted a multi-pronged approach to seize control of its silicon future. First is a groundbreaking new cooperation model involving its software unit, Cariad. In a landmark deal, Cariad is co-developing a custom system-on-a-chip with Tier 1 supplier ST Microelectronics. But the crucial, game-changing clause in the agreement is the stipulation that the wafers for this bespoke chip must be manufactured by Tier 3 foundry TSMC. This is a masterstroke of supply chain management. It gives Volkswagen direct influence and, more importantly, supply security deep within the value chain, ensuring that the exact chips it needs get produced for years to come. Simultaneously, VW is playing the field. For its most advanced automated driving functions, up to Level 4 autonomy, Cariad is sourcing high-performance SoCs directly from chip design giant Qualcomm. This dual strategy of co-develop and direct source shows a newfound sophistication, allowing VW to both create tailored solutions and tap into the best off-the-shelf technology, all while building direct relationships with the key players. Perhaps the most ambitious move is the creation of the European Semiconductor Manufacturing Company, ESMC, a landmark joint venture to build a new fab in Dresden, Germany. This isn't just a partnership, it's a co-investment, a strategic alliance to regionalize a critical part of the supply chain. The players involved are a who's who of the European auto-industrial complex and the world's leading foundry. TSMC holds the majority 70% stake, with automotive Tier 1 giant Bosch and semiconductor firms Infineon and NXP each holding 10%. The plan is to invest over €10 billion to construct a fab dedicated to meeting the future capacity needs of the European automotive and industrial sectors. The facility, which broke ground in August 2024, will produce chips on mature but critical 28/22 nanometer and 16/12 nanometer nodes, bringing production capacity physically closer to its end customers and creating a more resilient European semiconductor ecosystem. Across the Atlantic, American and German automakers are making similar moves. Ford, determined to avoid a repeat of the F-150 fiasco, has entered a strategic collaboration with US-based foundry Global Foundries. The goal is to boost domestic chip supply, jointly research and develop new semiconductors specifically for Ford's needs, including MCUs and ADAS solutions, and begin vertically integrating key technologies to increase its independence. It is a clear strategic pivot to de-risk from an over-reliance on Asia. Mercedes-Benz, meanwhile, has publicly shifted its strategy to include direct procurement from semiconductor suppliers. The luxury automaker has inked deals with companies like Wolfspeed for critical silicon carbide, Si-C power semiconductors, components essential for efficient EVs. By establishing these direct relationships, Mercedes is safeguarding its supply chain and ensuring it has access to the specific technologies needed to maintain its competitive edge. These case studies represent a fundamental rewiring of the industry. The old, linear chain of command is being replaced by a complex, interconnected web of strategic partnerships, direct sourcing agreements, and co-investments. The auto industry's scramble for silicon is a dramatic and necessary response to a crisis. But this new, aggressive playbook is not without its own significant risks. The road to a secure, resilient semiconductor supply chain is a treacherous one, fraught with financial, organizational, and geopolitical minefields. The entire industry is reacting with panic to a historic shortage. Car makers are signing long-term, high-volume contracts and co-investing in billions of dollars of new fab capacity. But what happens if this massive, synchronized push for supply collides with a softening of demand? The risk is a classic supply chain phenomenon known as the bullwhip effect, where a small change in end-user demand creates wild, amplified swings in orders further up the supply chain. After years of scarcity, analysts are already seeing signs that the chip shortage is easing, with some predicting a potential oversupply in certain segments by 2026 or 2027. If this happens, automakers could find themselves locked into expensive, non-cancelable contracts for billions of dollars worth of chips they no longer need. Today's solution to a shortage could very easily become tomorrow's crippling financial crisis, turning secured capacity into a massive liability on the balance sheet. Perhaps the most profound challenge is internal. Automakers are masters of mechanical engineering, logistics, and mass production. They are not experts in semiconductor physics, silicon design, or fab management. Their attempt to become fab-light companies, deeply involved in the design and procurement of their own chips, is a journey into uncharted territory, and one for which they are culturally ill-equipped. The automotive world operates on long, meticulous development cycles of 5 to 7 years, where the highest priority is absolute reliability and achieving zero defects over a vehicle's 15-year lifespan. The semiconductor world, by contrast, moves at a blistering pace, with rapid, iterative design cycles of 1 to 2 years. These are fundamentally different cultures. It is a real question whether a century-old hierarchical car company can adapt to the agile, fast-moving world of Silicon Valley. Ford's CEO, Jim Farley, candidly admitted that a key failure leading to the crisis was that his company simply did not understand the chip industry's technology roadmap. Closing this knowledge gap is a monumental task. It requires hiring entirely new kinds of talent, building new departments from scratch, and fundamentally changing institutional habits that have been ingrained for over 100 years. The risk of mismanagement, flawed technical decisions, and strategic blunders is immense. The single greatest risk, however, lies beyond the control of any single company. The new automotive strategy, by tying the industry's future to advanced SoCs from the likes of Nvidia and Qualcomm, has inadvertently made it more, not less, dependent on TSMC, and by extension, on the geopolitical stability of the Taiwan Strait. TSMC's global diversification is real and significant. Its new fabs in Arizona will produce some of the world's most advanced chips on US soil. Its joint ventures in Japan and Germany will bolster regional supply chains for critical automotive and industrial components. But these facilities are a hedge, not a replacement. The core of TSMC's most advanced research and development, its highest volume production, and its unmatched ecosystem of suppliers and talent remains firmly planted in Taiwan. Even TSMC's CEO, C.C. Wei, has spoken about the immense challenges and higher costs of replicating their Taiwanese operations elsewhere, citing issues with infrastructure, regulations, and the local supply chain. This creates a terrifying vulnerability. A Chinese military blockade or an outright invasion of Taiwan would not be a mere supply chain disruption like the one in 2021. It would be a catastrophic, full-stop event for the global technology industry, and by extension, for the production of the world's most advanced vehicles. The software-defined car, the data center on wheels, would be dead on arrival, its brain trapped on an island in the crosshairs of a superpower conflict.